Thank you, Dr. Balaji, for inviting me for this advanced training program to present here. So I hope you can hear me.
Yes, sir.
You can hear me?
Yes, sir, very much.
Yeah, okay. So I will try to share my screen for my slides. So I need permission, it seems.
1 second.
Yep. Yeah. So can you see my slides?
Yes, sir. Maybe you can go into a full screen mode.
So you are not able to see the full screen. Okay.
No, we are able to see other things also, like our notes and the slide deck also. We felt maybe nine.
Okay.
Yeah, yes, this is perfect.
Is it okay now?
Yeah, perfect.
Yeah, thank you again, Dr. Balaji. And so it's quite early morning here in France. So the objective for me when you invited me was to focus on privacy. But I thought that as this is the first presentation, I thought I could give you an evolution of the DNS protocol from plain text to how it has evolved in adding security as well as privacy. So I have number of slides. So due to time constraints, I will go a little bit faster. If you have questions, we can have it at the end of the session. So the agenda for this presentation will be that we will start with the DNS as it is, how it was designed in the early 1980s, and we will follow a DNS query response, what happens when a DNS resolution is done. So we will see how the query passes through the different places in the internet and gets back the response. Then once it is done, we will see how there have been efforts being done to add privacy into the DNS protocol. The next step is to look at how security layers are added to this DNS protocol. Finally, I will conclude with a tool called Zone Master, which we are developing with the Swedish registry, and how it could be used to verify the DNS health of your domain names. So already Dr. Balaji gave a short introduction about me. So I finished my engineering from the University of Madras, and I did my master's and PhD here in France. Currently, I work with the French Network Information Center. So it's called AFNIC, Association Française Nommage Internet et Coopération. So we manage the internet domain namespace for France. So officially, we are the .fr registry. We manage not only .fr, but also the domain names for overseas territories of France, like Martinique, Guadeloupe, etc. We are also the backend operators for different generic top-level domains like .paris, etc. Since we are managing the internet domain space for France, we are delegated authority by the French government to manage this space. And since we are doing this, we do have a lot of how do you say that, responsibilities with the stakeholders, such as the French government. We have other stakeholders like the African countries, which are francophone. We help them. We help them to manage the internet resilience. We do research and development. So at the French Network Information Center, we do have these activities to make the internet stable and resilient. As my other things, I also am LoRa Alliance Academic Working Group Chair. So LoRa is an IoT technology, and LoRa Alliance is a group of companies, like 500 companies, from Amazon to Google to Microsoft, which are part of this alliance to develop the LoRa technology, which is an IoT technology. It comes under the LPWAN, Low Power Wide Area Network group. So that's it. So let's get into the DNS. As you know that AFNIC, the French Internet Network Information Center, the core technology for us is the DNS. So we have an understanding of the DNS protocol and we work on it. So that's where my role here as a presenter comes into play. So as you see before, when you see before the DNS, so what we do see here normally in the DNS is the RFC 1034 and 1035 that explains the DNS protocol and specifications. So sorry for my explanation here, but just to have an understanding, I hope everybody knows already RFC's request for comments. So it is the documents, the standards developed by the IETF, the Internet Engineering Task Force. So before the RFC 1034 and 1035 written by Paul Moka-Patrice, the idea behind the DNS came in RFC 791. So it was in 1981. So as part of the DARPA development, the protocol, where the internet evolved, John Postel from the University of Southern California, once at that time, John Postel was the one who was managing the internet namespace. So what we see here now see as ICANN, IANA and all. So John Postel was a single authority doing all those things at the time. So when you know that, I'm sure that most of you know about DARPA and how the universities, the industries work together to develop the network protocol, internet protocol. So at those times, to communicate between each other, they did have the IP address and they needed the domain names. So, the domain names are for easy understanding for human beings to identify a network address. So at those times, they used host.txt, a file which was shared between each of these institutions when they were updated, and it was difficult for them to manage the host.txt file. So at that time, they wanted to have something that was more easier. So in RFC 791, the network protocol design ideas are discussed, and addressing and naming is one of the discussion in the RFC 791. And there John Postel says that, so he concludes, he resumes the internet in 3 sentences. It's like you want what you want to seek. So it's identified by a name, and the information regarding the name is in the address. So it's somewhere stored in the server, and it is the address that indicates where it is. So from the name to the address, you have a route. So you have to route from your name to the address to get this information. So he resumed it in such a simple way, which gives you an idea why DNS, even now after more than 40 years, is still the basic cornerstone of the internet. So if you see the DNS, it could be called as a mapping table, it could be called as a phone book of the internet. So if you come to the third point here, we have the identifier, the name, which is understandable, which is remembered by the humans very easily. And that name, it has to find the route where the applications are. For example, here the applications are the mail ID, the web server, etc. So it is identified by an address. So to go from the name to the address, you have the mapping table, which we call the naming service, that is the DNS domain naming service. So the domain naming service to work, there is an infrastructure behind it. Okay, so it's not just like in our phone where we just add the name and the telephone numbers. So there is an infrastructure behind it which works it so to make sure that the domain name is resolved wherever you are. You could be from the India, you could be from France, you could be from Australia. When you resolve afnik.fr, you will resolve to the same information wherever you are, whatever type of operating system you use Android, Linux, Mac, but it's the same information that is available to you. So that magic is done because of an ecosystem behind the domain naming service. So the ecosystem starts with the number one here. So the identifier is standardized. It not be something random, but it's standardized. So the ID identifiers, that is the domain name and the IP address, it is standardized by the ITF, that is the Internet Engineering Task Force. So the identifiers domain names, they have the system, and the IP address, they have another system. So for the domain names, we call the domain registry. And at the top, it is ICANN. So we had somebody from Samir and Gupta from ICANN presented early. So ICANN manages what goes in and out of the root. So we have like 13 root servers, and we have Anycast servers all around the world. So what goes into the root server is managed by ICANN. It's true that they have a multi-stakeholder ecosystem who helps them to manage that. And under that, we do have a layer where we call the top level domains. And in the top level domains, we have two varieties. One is called the CCTLD, country code top level domains, like .fr, .in. We have GTLDs, generic top level domains like org, .com. And under that, we have the second level domain names, and we could have multiple layers behind, down it. So the beauty of DNS is it's hierarchically managed, and it could evolve, scale, and it gives the performance. So in this domain namespace and the registry, it is managed in such a way that, for example, a name is not duplicated. So afnik.fr, there is only one afnik under the FR hierarchy, but you could have an afnik.com in another sub namespace. So that's how the provisioning is done. So this is what we call the route. In John Postel's sentence, we see a name indicates where it is, and route indicate how do you get to the address. So the route for the domain name registry, and similarly, you have for the IP address, you have a hierarchy where the top, like ICANN, the domain registry, you have the IANA, and under the IANA, you have a different layers. For example, when you in India or CDAC, they get the IP address, they get it from the local internet registry or from the ISP. But the local internet registry gets the IP address located by the 5 RIRs, regional internet registries. For example, in Europe and Middle East, we have the RIPE, Reso IP European. For in the Asia, you have EPINIC, Asia Pacific Network Information Center. Similarly, for each region, for example, for South America, you have LACNIC, Latin American Network Information Center. For Africa, you have AFRINIC, etc. So this ecosystem makes sure that the identifier, that the domain name is resolved to the IP address without any difficulties. So let's go to a classical internet use case. How do you do it in a classical internet use case? Is that a user accesses the web. So at the first, he types something in his browser, for example, http://cdac.in. He doesn't know what happens behind. There's a black box, and he gets the information, the website information of CDAC. So the first thing that happens here is a DNS resolution where you get the IP address of cdac.in. Then once you have got the IP address, a HTTP connection session is established to get the information. So this is the classical internet use case. So let's go a little bit into the steps. This is what the first point in the agenda where we are following a DNS resolution. So let's say we are typing iot.rd.nic.fr. The browser searches in its cache. So the browser always has a cache to make it performance. So whether it has the IP address of the domain. If the IP address is not found, what happens is it asks the OS operating system to resolve the IP address. In the OS operating system, you have a small program which we call the stub resolver. The stub resolver gets this information from the browser, saying that it wants to resolve iot.rd.nic.fr's IP address. So there are different sub programs inside the OS, which starts with nsswitch.conf, where it defines how this resolution happens. It has, for example, it has like files, DNS, etc. The files is the etc host.file. So it says by priority, it will go and look at the files, that is etc host. It looks at the etc host. It sees that it has only the names of localhost and Sandoche, but not iot.rd.nic.fr. Then it goes to the next resolve.conf. And in the resolve.conf, we have the IP address of our resolver. So for example, a normal user will have the IP address of his ISP, Internet Service Provider. But here we will, as a company, you can have your own name servers where you have your own resolver. So you go and ask this resolver to find the IP address of iot.rd.nic.fr. So what happens is that it gets into the resolver, and the resolver, it has to find the IP address of iot.rd.nic.fr. If the resolver doesn't have any information in the cache about this domain name, so what it does is that it goes and asks the root. That is the root service. The root says that, okay, I'm looking at a scenario where this root, or these are called authoritative name servers, and this name server doesn't have any information about this domain. So the root will say that, okay, I don't have any information about the domain, authoritative information about the domain name, but I do know that you can go and ask the top level domain.fr, who will have information about it. So this is called an iterative query, but from the user to the resolver, it is a recursive query. The recursive query is that you have to find the information, but from the resolver to the root, it's an iterative query because it finds only the partial information. So the step goes one by one until to the rd.nic.fr, and from where the IP address of the domain name is found out. So that is the authoritative information. So that is found. So if you see here from a Wireshark perspective, the Wireshark is a tool to see the dump of the packets that happens here. So there are multiple queries that is happening here. So 10.10.86.48 is the local private IP address that I have. And we have, this is 10.10.50.163 is the IP address from looking from our company's point of view, but it has its public IP address. So there is a up and down transaction happening until you get the IP address of the iot.rd.nic.fr. So this is how the resolution happens. So before the resolution to happen, there is a lot of discussions that is happening on that we don't see outside. So if you see in the Wireshark, it's how the datagram is constructed from the Ethernet frame to the IP to the UDP and DNS. I'm not going to detail. From a wire format, you have this is the packet form information. So the source address, the destination address, the port is 53, and the DNS packet where the query is for iot.rd.x. This is the transaction ID. So these are all, the yellow color is the one which shows which is important for the DNS packet. So in the DNS packet, you have a header packet and you have the payload. So in the header packet, we have the query name, the opcode, the ID, the query count. The query name is iot.rd.fr. The query type is it's asking for an address, and the query class is the internet address. So I'm not going deep into that. So let's see what happens. So the packet starts with it goes to the root, and in the root, if you see it creates a query ID. It has a question count. So it's a query, and if you see here, this is recursion desired. So it's a recursive query where it's asked for a recursive code. So that's what happens at the beginning. Then when you see the response, you see the recursion is not available, that is 0. So the query is, there is a response. But if you see there is no answer, so there is an authority count which says that these are the name servers that could have information about iot.rd.fr, and you have an additional count which says which are the IP addresses of these authoritative informations. So what I want to show here is that there's a lot of data and metadata that is being transmitted between a query and a response. So similarly, you go one by one. I will not go deep into that. So until you get the response. Okay, so this is what the answer count is. That so you have the final information. So the answer count is 2. And here it says that for this query, we have the response, that is the IP address that has been asked. And this is the IP address. And this IP address is obtained from the name servers ns3.nic.fr and ns2.rd.nic.fr. So this is how a query transacts from a web browser to the different parts of the internet and gets back the IP address. So it's a big black box for us, but what we have to see is that there are a lot of information out in the internet which we don't see. Now, until now, what we have seen is that how a classical DNS query response happens. Now let's go in a little bit into the privacy. So privacy is defined by Wikipedia as the ability of an individual or group to seclude themselves or information about themselves and thereby express themselves selectively. So if I want to look at it from an easier point of view, so to get an information, you need to identify yourself. That's needed. But do we need to identify to everybody all those information, or we need to identify only to a certain person to get this information? For example, if you are going to the doctor and you have a health issue, you want only the doctor to know that problem and get medications for that. You don't want the secretary of the doctor to know that. You don't want others involved to know about your problems. So similarly, in the internet, what happens is that everybody knows about your problem. For example, if you are going to buy something, let's say alcohol in the internet, if you search for a website and that website that you have searched is known by the top level domain, by the root server, by the second level authoritative name servers, all these people know that somebody like Sandoche has searched for alcohol in the internet. So is that necessary? So if you see this image, this is by Jeffrey Stern, who is a famous researcher at the Asia Pacific Network Information Center. he has done some measurements, and he shows that what we think is that we have a client, you go to the DNS resolver and you get the DNS response. That's not how it happens on the internet. There are a lot of, as you've seen in the Wireshark that I've shown before, there are a lot of other queries being done, and these stamps of information about you are there in the internet. For example, if you see here, this is from the TC dump of the root server. And if you could see somebody with the IP address, 2001 IPv6 address of 2001.67c.1348.8002 has asked for a query called armanpress.am. So for the root server to know this, it's not necessary. So, and another issue in the DNS is that all the information is clear text. So anybody can see what happens. DNS resolution, as I said, by this image, it's quite talkative. And your information could be used for business intelligence as well as surveillance. For example, if you see, we are searching for something in Amazon, for some product in your Google, then immediately if you see in your mail, you get a mail from Amazon saying that these types of products are available. So this is all information collected. So that's the business intelligence that happens there. And we know there are a lot of state actors who are using DNS information for surveillance. So there have been a lot of discussions in the internet. In the IETF. The IETF is the one which creates standards for all network protocols and above. And we know that the discussions had started for a while, and I will show you how this timeline has happened. But before that, what I would like to point from this slide is that, inference could be done from these DNS queries. So my colleague, who is a famous, is one who wrote the RFCs for DNS privacy. What he says, for example, is that currently, if you want to know what Pentagon does, you have to just go and sit near a pizza shop near Pentagon. And if you see there are a lot of pizzas being ordered by the Pentagon, and then you can infer that currently there is a war going on in Israel, and there is a support from Iran, and maybe Pentagon is trying to do something on Iran. So it's not the authoritative information, it's an inference that you can get from the data that you collect because of more pizzas being ordered from a pizza center near Pentagon. So that's an inference. Similarly, this is a paper from Princeton, which shows that based on DNS queries, you can infer what type of IoT devices that you're using. For example, these are the queries that we have on the right, and the devices that could be used at your home. So this gives more information about the individuals that are staying in the home. There has been a lot of research studies like that. Even there was an issue in the Dutch parliament where they stopped smart meters for a while because a research pointed out that based upon your electric meter at your home and the consumption, there can infer what type of series that you are looking in, whether you are looking at Netflix, what type of ideology you have, right or left. So these are all the things that could be inferred from this information. So that's why it shows that DNS queries could give a lot of information, data and metadata that could infer about a private individual that causes an issue in privacy. So if you see, with privacy, there have been 3 RFCs, and all the 3 are written by my colleague Stephen Botsmeyer at Daphnic. So the first RFC 7626 talks about the DNS privacy considerations. It mentions how the DNS data is out in the wild and how DNS cache snooping could be done between the stub resolver, between the user and the resolver, how the information could be collected from the naming servers and the authoritative servers like the root servers. Then he suggests an idea which could minimize the information that is out in the wild. It is called QName minimization, query name minimization. It is RFC 7816. It's an experimental RFC because if you know at the IETF, you have a standard variety, you have an informational variety, and you have an experimental variety. So after RFC 7816, there were a lot of research being done on QName minimization at an operational level. People have implemented that. There are also academic papers, and based on these feedback, RFC 9156 updates the DNS query name minimization RFC, which obsoletes RFC 7816. So what does QName minimization does? When the iot.rd.nic.fr, it goes from the stub resolver to the resolver. So the resolver knows that the guy behind 192.134.4.85 is interested in iot.rd.fr. But the resolver doesn't send the complete query during the iterative state. It sends only FR to the root. It says, okay, do you have information about FR? And the root says, yeah, you can go to the tld.fr. So similarly, the metadata that is sent with the query is minimum. So thus, like what I have seen earlier, the root server doesn't have information about iot.rd.nic.fr is asked by who. So query name minimization minimizes the amount of data which has been out in the wild for DNS resolution. Now, how do we configure QName minimization? So as you all know that DNS, there are a number of DNS softwares which uses the same protocol. So we have bind, unbound, not, and others. So in bind, for example, if you want to add QName minimization, you have different options like relaxed, strict. When it means strict, if the resolver that is getting your query doesn't use query name minimization, then the resolution doesn't happen. If it is relaxed, the resolution happens even if there is no query name minimization configuration in your resolver. If it is off, it is a normal DNS plain resolution. Similarly, in unbound and not. So I did a small test with the dig. So I tested with two name servers, government name servers in the internet. For example, ns2.winavi.net is for Telangana. Is for Telangana, I think. So I tested whether they have the resolvers, the open resolver, whether it uses QName minimization. If you see, I use the QName test domain to test it. QName minimization is not enabled. So they don't have this option enabled on the resolver. But I did another test with, for example, the open resolver by Maharashtra government. So you see QName minimization is enabled. So you can see which resolver to use if you don't want more information of yours to be on the internet. Now, there is another test, that is another study that was done by Princeton. In Princeton, to improve privacy in the DNS, they used a concept called oblivious DNS. So the idea is to obfuscate the information that is out in the wild, as we have seen earlier. So what happens here is that when a client issues a DNS request, the stub resolver here you see, it generates a session key. It's a symmetric session key. It encrypts the domain name with the session key. So if you are asking, for example, afnic.fr, it encrypts that domain with that session key. Then it sends that information to the ODNS resolver, public resolver. To do that, it adds with afnic.fr the ODNS suffix. So once it is done, it sends it. The stub sends the query to the recursive resolver, which then sends to the authoritative name server. These are the authoritative name servers for the specified ONS domain. So these people doesn't know because it is encrypted which domain name is being asked, but the ODNS resolver will have information because it has a symmetric key to encrypt and decrypt. So it is also added with the public key. The ODNS resolver gets all this information and it responds back to the ODNS stub. So all these people, they don't have information on what query and what the IP address that is behind that query. So Oblivious DNS has been there for a while. It has some issues of operational implementation. As I understand that some like Cloudflare are using Oblivious DNS. They have support for Oblivious DNS. But I don't have much more information. But it's a method also to improve privacy in the DNS. So we've seen the DNS clear text, what happens. Then from a privacy point of view, there are two options here where we have query name minimization as well as Oblivious DNS. If I'm going above my time, please tell me how much more time do I have, Dr. Balaji? Pardon?
15 more minutes.
I didn't hear you clearly.
Hello. Yes, sir. 15 more minutes, sir.
15 more minutes, so I will go fast. Okay. So now we will look at it from a security perspective. So if you see from a security perspective, what happens is that here it's the DNS resolution, and then here is the information. You get the web site. So attacks could happen here, such as the Kaminsky birthday attacks, which is called DNS cache poisoning, etc. Here also attack could happen. So where you have, for example, here the security is done by TLS, transport layer security, and you have the certificate authority. And if you compromise the certificate authority, you might be able to compromise this resolution. So as you know, DNS spoofing is that, if, for example, you poison the cache with some other information, that is, when you are asking for afnik.fr, before the afnik.fr gets into your resolver or your stub resolver, you can do a man-in-the-middle attack so that you can identify the transaction ID and send a false IP address back. Or you can poison the cache by putting another IP address in the name of that. And then you spoof the resolution. So to counter that, we had a DNSSEC. So in the DNSSEC, I will not go much into the detail due to time constraints. So the idea simply is that you have the, for example, you have the address record 192.68.0.1. You have also a encrypted version of that address record. So once you get back into that, you compare the IP address that you obtained is the same based upon DNSSEC. So there is a method, so it will take time, but you have a trust chain that is being created. And if you want to compromise with DNS, you have to compromise the complete trust chain. So that's a little bit difficult. And similarly, the verification is done based upon this trust chain. So DNS trust chain, DNSSEC, what it adds is that it doesn't encrypt. What it adds is that it makes sure that it enables you to validate the integrity of the information that you got. So you have a clear text information, you have an encrypted information. So you compare the clear text and encrypted information to validate the integrity of your response. So this is how, I will not go details due to time constraints. So DNSSEC, we know what we understand here is that, so it adds a security layer where you can make sure that the IP address that you obtained is the correct IP address and it is not spoof in the middle. So that's the capability of DNSSEC. But there is another attack scope here where you have the certificate authority. If for example, we use the certificate authority to get the, for example, the IP address, it is certificate by the certificate authority kinetics, and this is the fingerprint of the certificate authority. The problem with the certificates authority is that in your browser, there are about 1024 root certificate authorities. So these root certificate authorities stamp the information with for example, this is validated by me. If I have to go more clearly, it is like, for example, if you go with the passport to a customer, to an immigration authority, it's the Indian government that stamps that the Sandoche Balakrichenan and the photo is validated by the Indian government. Similarly, afnic.fr, the IP address is validated by Kinectix. But the problem here is that there are 1024 root certificate authorities, and if you are able to compromise any one of them, you can compromise the complete resolution of the web service. So this already happened, where there are famous attacks like Komodo and DigiNota attacks. What happened is that, they have a compromised certificate authority, and based upon the compromised authority, they were able to get credentials for Google Mail and all, and they were able to see the real Google Mail. So this was done during DigiNota. State actors were involved. So the IETF started discussing it, and they came with a response which is called the DNS authentication of named entities. So the DNS protocol is already in implementation. It is currently more used in the mail scenarios. In web, it has not succeeded because due to performance issues. So the browser vendors like Chrome, Firefox had some plugins really, but they stopped those plugins and they are not deployed in the browsers. But there is currently a working group which is called DNS Authentication of Network Clients Everywhere, which is trying to see whether DNS could be used in other scenarios, not only for the mail. So what does DNS do is that, for example, it has a fingerprint of the certificate authority. So that's called the TLSA resource record, Transport Layer Service Authentication Resource Record. And if you see, for example, what happens is that you can, once you get the certificate, you ask the DNS also about the fingerprint. So you validate the certificate with the fingerprint that is obtained from the DNS. So thus you reduce the scope. If you are only compromising that single authority, you will be able to compromise this resolution. Otherwise, you will not be able to compromise. Like earlier, if you compromise any of the one root certificate authority, you'll be able to compromise. So that's the difference here. So I'm not going deep into that, but what happens is that the attack scope is reduced. So you could compromise only by attacking the particular certificate authority. So with DNSSEC and DNS, security is added to the clear text data communication done by the DNS. Even for IoT purposes, now it's being used. It has been updated in TLS 1.2 and 1.3 for mutual authentication here. So when you do the TLS handshake, the server and the client both can ask for DNS indication. When I say DNS indication, not only for the asking for the IP address, that is the A, it will also ask the TLSA resource record, which is a fingerprint of the certificate authority, thus enabling you to validate your HTTP or certificate information. So another thing that you see here is that in the RFC 7626, which it talks about the DNS privacy considerations, it looks at how DNS is too talkative, and also there could be different occurrences. This is one that I got from a colleague. So for example, he tries to resolve ether.com.tr using RIPE Atlas probes. So one of our earlier presenters were also talking about how to look from India from a different angle of from different network spaces to identify how the resolution is done. So it is already done by RIPE Atlas. So RIPE-less, it's free. You can ask RIPE for nutless probe, and you can put anywhere. So, and you can also use the RIPE-less to do measurements from the different parts of the world to have a look at how things happen. So he does that about 500 tests. And if you see that out of the 500 tests, for the same domain name, there are different IP addresses. There are 5 occurrences of different IP addresses here. There are 6 occurrences of different IP addresses here. So that is called the lying resolvers. So there are certain resolvers, when you ask them, they lie the information that, and then they try to snoop you. So here also, if you see, he did the same. There are about 498 probes, and 463 probes were giving the correct IP address, and the other 6 probes were giving refuse or serve fail. So there are some type of hijacking is done, or information, or it is being restricted. So I think ether.com is some domain name which was sensitive in Turkey at that time. So that's where my colleague did this experimentation. So what we want to show here is that resolvers can lie sometimes, and may allow you to snoop. So this is the DNS encryption timeline. I'm not going deep. So this is how things have been done. So I will go to the how. Now, until now, we saw minimization, Core name minimization of oblivious DNS for privacy. We saw how DNSSEC and enables security, but the information is not encrypted yet. It's always clear text. To encrypt, there are 2 protocols that has been added, which is called DNS over TLS and DNS over HTTPS. So DNS over TLS, what it does is that it does the transport layer service thing, not only for the HTTP resolution, but also for the DNS resolution. So there is a secure handshake that has been done earlier to make the communication encrypted. So this is how a classical classical TLS handshake happens. And once you have the certificate being added, then the DNS query and response is done. So if you want to configure dot, you have to do this. The left side is for bind, and the right side is for unbound. So you have to add the full chain, and then you have to listen on port 853. So that's how web dot communicates. Similarly, in unbound, you need to have a forwarding resolver which uses which supports dot to do that. Okay, so I tested with the Cloudflare for me, and I saw that I was not supporting DNS over HTTPS or DNS over TLS. So then I added the configuration in my browser, and I could see that DNS over HTTPS and DNS over TLS is supported. Then I did a test with my with the KDIG. It's a not dig, and what I could see that all my communication is encrypted. Similarly, if you see from Wireshark, you see that the TLS handshake happens, and then the communication here, you don't see the domain name. So there are problems with dot. One is that it uses a specific port 853. So the middle boxes can block it or identify that anything that goes, it's encrypted. So that's an issue, and performance is also an issue. As you add security, DNS is a datagram UDP layer protocol that is mostly used, and it has been used for a purpose to enable performance. But here performance comes in problem. With the DNS over HTTPS, the advantage is that there are no 2 layers of handshake that is may happen. It's a single handshake, TLS handshake, both the DNS resolution and the HTTP resolution is done. So that's how DNS over HTTPS enables and adds reduces the performance issue. So if you want to configure DO, for example, you can do that in your Chrome. You go to the settings and the security DNS. As of now, you can use Cloudflare, Google, or your own private DNS resolver, which supports DO. And once it is done, you can have normal secure encrypted communication. For example, here, if you see, you can see all the information that is without though, what I'm asking, how it is being done. But with the though being added, I could encrypt the payload. There is an issue here. So I tested with Quick. Quick is another protocol that's also encrypted by, it has been developed by Google. Normally here, if you see, it should be though, but I had a wrong screenshot here. So with though here in the place of though, a Quick, it would be though. So that's how it is there. So finally, so what we have seen until now is that DNS is the plain text, adding privacy with QNAME minimization and oblivious DNS, showing that the integrity of the DNS responses are correct. So we have DNSSEC, we have reduced the attack surface in the HTTP using DANE, then added encrypted communication with DOT and DO. So how do we test it? So, DNS is a peculiar thing, like it's similar to our body. For example, in our body, we could have certain issues somewhere. For example, you could have diabetes, you could have kidney, but still you will be living. But if you want to make sure that you are completely correct, then you need a complete health check. Similarly, for DNS, you will be accessing the information even if there are certain issues, but it might cause problems somewhere. So that's why you need to test all the different issues, for example, connectivity, delegation, name server, DNSSEC, all this. So like in the health check, you need to have a testing of different subtopics to make sure that your DNS resolution is completely correct. So this is how you do with a normal test with a normal tool, basic tool. But if it doesn't have information, it will get only no error, next domain, etc. But you could use ZoneMaster. ZoneMaster is the tool developed by Afnik, my company, as well as the Swedish Internet Registry. We have been developing it for the last 10 years. And I could say with all humility that it is the best tool for a comprehensive health check in the world. So you have the complete information and it is updated. There are about 4 or 5 people, dedicated people working on it. And with each evolution of the DNS, those things are updated in the ZoneMaster. So you see, you have the different subtopics that we test. It's completely free, open source. And you have a different ways of getting this information. You can use the CLI if you want to. If you can use a Zone GUI like zonemaster.net. If you want to have your own database and all, you could use that. You can test thousands of domain names using the batch method. So there are different outputs, and you could get statistics. So I'll go a little bit speed so that I'm on time. So here, this is how, for example, I tested a domain name where you can see that the domain is resolvable, but there are issues. Connectivity, for example, if it says that over TCP, you don't have connectivity. So when you resolve over UDP, you might get the information, get a response back. But when it falls back to TCP, you might not get the response back. So similarly, you have a DNSSEC issues here. In the delegation, for example, the child does not list enough name servers. So for redundancy purposes in DNS, you should have at least minimum 2 name services. So this is not happening here. Similarly, here we have another test which shows that there are errors in DNSSEC that could cause real serious issues. So with ZoneMaster, it is possible for you to identify different issues with your DNS zone. So sorry, I had to go a little bit fast to be in time. I hope I was clear. If you have any questions, I will be happy to respond.
Yeah, thank you, sir. Any questions? Right, so it appears there are no questions. Thank you for walking us through the complete evolution of the DNS protocol from its plain text nature to the secure and privacy aware nature, which is the present state. Thank you very much, sir. Vale sir has left for joining an urgent meeting. So we'll be getting back to you, sir. Thank you very much.
Thank you.